All right, welcome everyone. So it's no surprise to anyone, the classes, like the seats here are thinning out. I don't know if people are actually just planning on not coming and dropping soon, or if they're actually just watching videos. Either is fine, but I may open the floodgates at some point and start letting the masters section sit here. I don't think it's quite ready yet. That would be a little bit crazy, but maybe we'll see how that goes over the course. The 688B section. You're not supposed to be here if that's you, but we'll see. We'll see. All right. So today we're going to talk about relational data. Before I do that, we have a few announcements to make, kind of general announcements about some sort of rule changes, I guess, but also something about the homework and everything too. So the outline will talk about relational data. We're going to cover sort of an overview of what relational data is. And notice I'm saying relational data here, not relational databases, because there is actually a difference. And this topic is much more about the data part of it than the actual databases. We cover almost nothing about how the databases actually work. We're going to cover sort of what relational data actually is and how you manage that. Then we're going to cover entity relationships. We're going to cover pandas and SQLite. Those are two libraries that you'll use in your next homework to handle relational data. And then finally, if we have time, I expect we will not have time, so I'm going to finish this last one up, or even more than that, next class. But we're going to talk about joins at the very end, sort of one way of combining data from multiple tables. OK, before I start, some quick announcements. The first thing is that the lunch sign-up is online. Does everyone know that? Most people do. Very few people have signed up, so that's OK. If you don't have lunch with me, it's certainly fine. I'll sort of hide my shame and be sad about that. I was hoping that a free lunch would incentivize people, but maybe not. No, but it's obviously, of course, optional. But just know that it is up. So if you want, I think there are 2 people signed up today. So we will go after how and have some lunch. If you want to sign up right now, I guess you can. I don't know what we'll do if like 10 people sign up during the course. We'll sort of randomize over them or something like that. But you can, but you can also sign up for a later one if it starts to be a lot of people signing up right now. We will create some additional ones if necessary, but so far it doesn't really seem to be necessary, so that's fine too. Homework 1 due, I think everyone knows, at Wednesday night at 11:59 p.m. We'll probably give you a few more minutes than that, actually, in case you're having some last-minute submission difficulties, but the official deadline is exactly midnight. But just to make it clear that we meet midnight on Wednesday night, we're saying 11:59 p.m. on Wednesday night. That's Eastern time. It's our current time. There's a bunch of questions on students switching from 388 to 688, so that's allowable. And now that the add deadline, which I believe is today, is ending, you can do that now. So I'm gonna handle it on Wednesday, just so we handle it all kind of in one batch. I'll post something on Piazza on Wednesday for all those students that do want to switch, and we'll just immediately kind of modify the class sizes and switch you over in one kind of little move. If you want to later, that's fine too. For now, just keep doing the assignment, the 688 assignment, and we will switch you over this Wednesday. Unfortunately, it's kind of a pain to do during the add period, because that means we have to have that much margin for the different classes. So it's actually quite difficult to do. So we're going to wait till afterwards. I'll sign whatever forms. I'll even take them if you need to get them signed by the dean or something. We can even take them elsewhere, but I don't think it's needed. I think it's a simple switch. So we'll handle that on Wednesday. The last thing I want to say before I get into some other philosophical issues is, one, we got a few questions about the homework and sort of the overall nature of the homework. So one thing you'll notice in the homework is that just watching the lectures is not going to be enough to do the homework, right? You're going to have to read the documentation that's specified in the homework. You're going to have to probably do some Google searches to figure out what you might want to search for besides just what's in the class. The goal of the lectures is to kind of give you the basic outline of kind of the overall knowledge you need to start knowing where to look. But then you are going to have to find extra things and find other sources. You know, the documentation that we provide hopefully is enough, but if you're confused about any part, certainly other sources are fine as well. So just be aware of that. I probably, in the next version I teach this, I will mention that more up front in the first lecture. As I said, there's going to be changes during this course. So just be aware of that. We know this. It's not unintentional. It's intentional. So if that is not what you want out of a course, then this is probably not quite right. And I would also maybe even argue that well, no, I shouldn't say the data science is not right. But you certainly, as a data scientist, you spend a lot of time looking up documentation. So if that's just horrible, you might want to think long and hard about that. Okay, so that's just sort of a little aside there. So, but now I want to move to a couple other things that have been happening. There are going to be little changes to class policy. So the first thing we've noticed is that a lot of people are posting on Piazza, either asking a question that's already been answered or asking a question that is answered pretty directly in the write-up. And actually, this is fine. I mean, so far it's fine. But I think that my class policy might be encouraging this, actually, because people seeing both, they get immediate feedback and they get credit for class participation. So it's a win-win situation, right? So I think this is probably my fault for making that policy in the first place. So I'm going to try to amend it a little bit to change that. And we'll post these updated rules on Piazza, and also include. Still also asked to include statistics on, what's the current mean of how many people are posting, etc. We'll post that about monthly to Piazza. So here's the new rules, and we'll probably finalize these. These aren't going to apply retroactively. They're just going to apply going forward. So don't worry if you've already done one of these. Don't worry at all. But we're going to make a few kind of requirements on Piazza posts. The first one is you have to use a search function before you post. I know there's a very long list of posts there, but really try to use the search function. If you post a question that is directly answered by another question, you will actually get negative points for this going on forward. Sorry about this, but there are a lot of questions where there's a one-line TA answer that just says, look at this other post. And again, it's fine if you did it already. I think actually we probably encouraged it a little bit, but from now on, use the search and try to figure out all the information that's already there on Piazza about the question that you're going to ask. Secondly, and also I'm not quite sure, I might mention the second right now actually, but we're going to change things a bit. I'm not quite sure how yet to make you get more credit for answering a question than for asking one. People have been answering questions, which we really appreciate. For the most part, they're all correct. We sometimes verify them. Sometimes we actually don't even do that because it's resolved. But to those that are doing this, we really appreciate it, and we want to encourage that more. So we're going to try to change the rules a bit to encourage that more. Number two, if your question relates to your code directly, so you basically copy a piece of your code or have something very specific to your code, do make the post private, because the idea is we shouldn't be looking at each other's code, and if you're posting your code for everyone to see, then that they would not be able to avoid looking at your code, so we don't want to do that. Third, and this is a little bit, there's a gray area here certainly, but please don't post just a large dump of your output and say, what's wrong with this? The goal of Piazza is sort of not to just sort of have everyone look at your output and figure out what may be wrong with it, but it really is more to kind of ask topical questions and kind of ask high-level questions about what might be wrong. And so if you're just confused and don't know what's going on here, try to formulate your question more as a question about the type of results you're getting and what's happening with your code, rather than just pasting the output. It's also not very useful for us to look at, right? Because we can't really understand from a big JSON string what's really happening. I do want to emphasize, though, I know that I worry a little bit about saying this, and I think I erred too much on the other side. I do worry about people not using Piazza if we make all these rules, right? That you're just sort of nervous that the question is going to be some of the question. Please don't worry. We will not, if you make an effort to try to find through a search, and that's okay. We'll understand. We're not going to be crazy here. But if it literally the same question appeared, the day before, then we'll dock you. But you can probably make up the points by answering other people's questions. So it's sort of all okay. But please do ask questions. I mean, we really do want that. We try to keep on top. There's a lot of questions. We try to keep on top of it. But we do want to use the resource. Answer the questions too. That's really helpful when you do answer each other's questions. That's very useful. But these are sort of some general statements. Any questions about this? Again, I don't want to appear like we're discouraging anything, but we also want to be able to conserve sort of TA effort. There aren't many TAs in the course. We're going to conserve TA effort so they can address the questions that are sort of most useful to address. Okay, so the last thing I'll say is yesterday the auto grader went down for, it was like 6 hours or so, something like that. And what happened was, this is sort of a choice we made, is that and people picked up on this in different ways and decided what to do with this different ways, but if you looked at the auto grading code, it wasn't very hard to write outputs that would just dump the so-called mystery web page in your output of your file, right? We actually knew this was possible, so we were sort of okay, just try not to do it, but maybe it's okay. But actually, someone also discovered that you could, and we thought we had a circumvention around this, but it wasn't functional for for our fault. But you could actually also dump the solution code if you wanted to by importing OS, the module OS, and then searching the tree for the solution code. Now we can actually find people to do this, right? Because all the code's logged there, so it's not very hard to find people to do this. The person that did, I think, was was not trying. They were trying to find this vulnerability and let us know about it. So that's certainly fine and much appreciated. But I think the end result is that what we're going to do is we're probably just going to limit the amount of feedback you get from Piazza. We're not going to dump the exact traces anymore. You can't print arbitrary code anymore, which I know is going to be a pain because some people were already finding the output too sparse. They were already having trouble debugging it so far. It's only going to make it farther or harder. So this is kind of a trade-off where we struggled with a little bit, and we decided to go one way, and I think it's not quite working. I think it's not. We need to go a little bit the other way and see if that will work better. So from now on, and for future homeworks, we're basically not letting you just print everything. We are giving only certain feedback and certain classes of feedback to the problems. So what this means is people are going to have to write more tests for their own code. And our examples we provide some of that. But certainly it's always a good idea, whatever code you write, to write as many tests as you can for it. And essentially the tests should validate the assumptions that you're making on the results you're getting to make sure they actually match what the assignment says and what you think they are doing. So it's hard. I mean, this is sort of a very vague statement in some sense, because it just says just test your code to make sure it's correct, right? And that's, oh, no problem. We'll just do that instead. So offering a few concrete examples here, one big problem people are having on the homework is that they're listing, when they call the Yelp API, they're querying all businesses, not just all restaurants. And this has been asked a lot on the webs on Piazza. I think it's causing a lot of people's questions about this because they seem to get too many results. There's all this weird formatting of the results, but it's all boiling down to the fact that you're just requesting all businesses and not just all restaurants. So that's pretty clear in the assignment. We think. If it's not, we're sorry about that, and hopefully this will clarify it. But those are the kind of tests you want to write. So when you execute your code, and you can run the queries yourself, right? Make sure that when you get the results back, they actually are only the restaurants and not all the businesses, and things like that, right? So little checks on your code that verify that what you think you're getting back is actually what you're getting back. And hopefully, I mean, it's easy for us to say this in all knowing about this, right? Knowing what the answer should be, but hopefully just kind of keeping that in mind will help you write better code and develop better tests for your own code, and hopefully mitigate some of the problems they're going to come up with. I know this new Piazza being more vague, or sorry, new AutoLab being more vague. So that's the policy going forward. As I said, this is sort of an experiment. We're experimenting with these things. We're trying to find the right balance here. Hopefully that is the right balance, but let us know in your feedback, I'm sure you will, what you think about this. And we may adjust going forward as well. We just have to figure out the right balance here. Okay, any questions? Yeah. We're trying to find, sorry, the question was, I'm going to try to repeat questions because I was asked by a few people on the online thing to repeat questions after I asked them. Just if I don't, wave at me and remind me to. The question was, are there going to be more TAs? We're trying to add some more TAs. It's not that easy to find TAs at this point, unfortunately, and the class got much more people enrolled than we originally thought. We're hoping that we can, I think, but we don't have any definite answers yet, so I don't know. Is the short answer. And one is actually only a half TA, so 2.5 TAs for 300 people is not very much. And yes, hopefully we can add more, but it's not definite yet. Okay, so let's jump into relational data. As I said, this lecture is on relational data, not databases. We will cover a database, very simple database, but really it's about the data itself. Out of curiosity, who here has taken a course on relational databases or something like the calculus of relational data? Okay, so for some people this is probably going to be very basic, but this is at least, in my opinion, kind of what the minimum knowledge you need to sort of use relational databases or use data that's organized in a relational way. And I also have to apologize beforehand to people like Christos Faloutsos and Andy Pavlo, who are actual database experts in the computer science department. I'm going to, I'm sure, oversimplify things to a huge degree and irk them, and they'd be pained to watch this, but I have to apologize. I only have one lecture to cover all of it. Well, maybe it's probably going to bleed into the next one too, but still, not very much time. Okay, so let's talk about relations. For lack of sort of a better way of putting it, a relation is a table. All right, and so when you think about relations, think about tables as your sort of canonical way of what a relation is. So a relation is some table that has columns and rows. And we call the rows in these things either tuples or records. They're a single instance of this relation that the table describes. So in this case, this could be a person relation. It describes people involved with this course. You didn't know, but Bill Gates and Elon Musk are also auditing this course online. I wanted to learn more about data science, I guess. The table itself has certain columns, but each row in the table is called a record that indicates, an element of that relation. So that row has ID, person ID 2, last name Wong, first name Eric, and he is a TA in this course. Now, importantly, rows have to be unique. The whole row as a whole has to be unique. And we'll talk about how it's enforced in a second. It's enforced with primary keys, but in general, the row itself, you cannot have duplicate rows in a relational table. The columns in a relation are called attributes, and they specify some element that each of these records or tuples contains. So each of these records or tuples contains a last name, a first name, and a role in this case. All right, so hopefully this sort of appeals to the intuition you already have. Everyone, I presume, has opened up a spreadsheet before. It's just that's what a relation is. It's a bunch of records in tabular form. They just call them relations because we like to be formal in computer science. All right, so let's talk about that in multiple tables. Of course, a single table is actually quite interesting already. And there's plenty of analysis that often is done using literally, you just take one big table, do some analysis, and then you get some interesting science out of that. That happens all the time. But where relational data really kind of shines is in its ability to represent connections between different tables and different sorts of relations. Okay? So let's take this example here, where I have my relation with an ID. And I'll talk about what IDs mean in a second, too. They're sort of have a special meaning in relational data. We have an ID, we have a last name, first name, and their role. Are they an instructor, a TA, and a student? But this role field's a little bit odd, right? Because what sort of data type is that? It would be my question, right? We could encode it as a string, right? But that sort of seems like it's missing something because we could put anything we wanted there then. And we really want this to always be one of three things, or maybe we could add more later, but for now just consider three, where it has to be an instructor, a TA, or a student. And so a slightly better way of encoding this would be to have a separate table. So we would drop this from our table and have a separate table that actually encoded the roles that were possible in the course. So we're going to have a role now, and the role has its own ID. It's 1, 2, or 3, and those correspond to instructor, TA, or student. And now, instead of having the text of our role be in a table, we're going to put a link to the ID of the role of that person. Okay? Now, I'm going to cover what these things actually are called. All these sort of references are called in databases. And there are really just two types. There are really two things that are the most important. So the first thing I'm going to mention is what's called a primary key. So a primary key is a unique ID for every record or tuple in that relation. In other words, every row in the table has to have a unique identifier, which is called a primary key. And that is sort of a guiding principle behind relational data, and that should not be violated. You should not ever lack a primary key in your table. I think most databases won't actually let you do it. So you have to specify some primary key in the table. So these things, in this case, the ID field, both for the person table and for the row table, that is the primary key of those tables. So they are unique, and they have to occur for every entry there. The second important type of key is what's called a foreign key. So a foreign key is an entry, an attribute in a table that points to the primary key of another table. Okay? So this element here is, as of itself, has no real meaning, right? If I dropped this table and got rid of the role table, this would have, I mean, maybe you could figure out that, the TAs are all in the same group and that I'm in a separate group and then all the students are in another group. But it would have no actual real meaning in the data itself, right? So it only has meaning in that it relates to the primary key of the other table here. And this is actually almost it in terms of how these databases are kind of organized structurally. Though we'll talk about in a second that there really are a lot of things you can do with this. So there are a lot of relationships you can encode with this notion of primary keys and foreign keys. Now, one important element here, which I'm not going to really cover in this lecture, but it's important to keep in mind here, is that databases require that everything, all these pointers to foreign keys, these foreign key pointers, at least in theory they require this. In practice, they often just ignore it because it's easier to ignore it. But in theory, they require that every foreign key here points to a valid entry in some other table. So if I were to delete my role of, say, a TA, right? If I were to delete this entry in the table here, that would now invalidate this foreign key. And I have to do something then. So there are all sorts of sort of things you can do. Sometimes you fill it with none values. You might actually just delete those rows, because if you delete the role, you might as well just delete all the people that are of that role, because that's conceptually what you've done. But just be aware that in order for this to really be a relational database or a relational system, you need to always have kind of valid links from a foreign key to another primary key. Any questions so far? Yeah.
This is a relational database, right?
Okay, so the question was, is this a relational database? So I want to be sort of clear here. So this is not necessarily a database. So there are three terms that I'll sort of want to define, though I will try to, I admit I will be somewhat cavalier in using them. The first is a relational database management system. And that is software like PostgreSQL or MySQL or SQLite that we're going to use. So the database software is called an RDBMS, right? A database is an actual set of data built in one of those database management systems. Okay, so that is a database. A database is, student records is the database. Okay? And more broadly, though, the relational data, the way I'm going to use it at least, is kind of the relationships that are implied by this and could be in the form of a database, but could just be in tables in a spreadsheet too. So if we have these things in a spreadsheet, I would still call these relational data, but it's not really a relational database because you can't execute the queries on it. So hopefully that isn't too confusing. You can use them somewhat interchangeably because it's how people kind of talk colloquially. But I will say that if these things are in two spreadsheets, that is still relational data, but it's not a database. Yeah? Can you also call it what data?
Structured data.
Structured data. So the question was, can we also call it structured data? Sure, but I think relational is a little bit more specific in terms of what it actually, the implications of what that means. All right. So the next thing sort of that underlies basic relational data, and this is really actually now moving to relational databases. This is now actually moving to how they're actually encoded in a database. Are something called indexes, and indexes, and it's not indices, it's actually indexes. When you use indices, it's fine, but the plural of index is indices, but these are index as an actual noun, and so for some reason it's pluralized as indexes. That's just how it goes. So what indexes are indexes are a way to find data quickly in a table. Okay? So let's just take an example here, and I think the example is actually much simpler than thinking about what these are structurally. So let's think about this table here, this relation, And let's think about what we would need to do if I want to find the entry, or possibly entries, because this term doesn't have to be unique, but if I want to find the entry or entries that have the last name equal to Gates. Right? All you could really do here, and so think about how this data is stored, right? It's just stored in some sort of text or some other format in an actual raw file. Maybe it's aligned to the axis to certain locations. Maybe it's not. But how would I actually go about finding the last name Gates? And if you only have the data kind of stored more or less in a flat file like this, it's very hard, right? You can't really do anything except just scan through every single record and check, is this name equal to Gates? Nope. Is this one equal to Gates? Nope. OK, is this one equal to Gates? Nope. And then find, keep a record of the ones you find and then return that. And that's a big O of n operation, where here n, and I'm going to use these sort of big O notation I'm not defining n here, for example, but here n is the number of rows in the database, right? So you have to, in order to find all the entries with the word Gates or the last name Gates, you have to scan through every element in the database, which is going to be a big O of n operation. And what an index does is an index speeds up that process. So let's look at what's actually going on behind the scenes here a little bit. Not really, but a little bit. So what's really happening is that this table is stored in some file, like I mentioned before, and every element of that, every row of that table just occupies some position in that file. All right, so let's assume that it, maybe we say we use 4 bytes for the ID and 4 bytes for this ID, and then we use 46 bytes for each fixed length of 46 bytes for the last name and the first name, and so we have exactly, conveniently, have exactly 100 bytes per record here. And so in our file, in the actual file we have, the first entry starts occurring at location 0, the second one at location 100, 200, et cetera. Okay? So all an index is an index takes a column and think about it as sorting it. It doesn't quite do that, but think about it as just taking your column and you sort it. Right? And each column or each entry in this index contains first the sorted list of the attributes. And for each one, it contains a pointer to the location where that occurs in the actual file, the raw file, not the key or anything, but the actual raw file where that occurs. Right? Now, it's not really a sorted list, but they do it slightly differently. But this is the basic idea of what's being done here. And the nice thing is with a sorted list, it's much easier to search in a sorted list for a name like Gates, right? All you do is you can do a binary search. You sort of start in the middle, saying, is that bigger than or less than Gates? If not, you look in the first half and you repeat that way. And now all of a sudden, finding the entry or entries that have Gates in them would be a log n operation. I guess that assumes that that is assuming that not every entry has the last name Gates. In that case, you can't do much but just return them all. But if there's relatively few of these, a constant number of these, then finding all of them in a sorted list would be a log n operation. And that's what an index is. That's really all it is. It's just a way, basically through sorting, of quickly finding the location in the file where those records actually occur. Now, they don't actually use sorted lists. Those aren't that efficient from a disk and memory standpoint. They actually use something called a B tree, which is a sort of a sorted tree data structure that includes multiple nodes or multiple keys at each node, so that you can load them efficiently from disk and kind of use your cache efficiently. But conceptually, they are just a sorted list, is what they're really happening. And you're reducing the time from being linear in the time it would take you to scan through the whole thing to logarithmic. Yeah, so I say it here. So importantly, the primary key of a table always has an index associated with it. So we always index the primary key, and that lets us quickly retrieve records based upon that primary key. So we always have at least that one. We always are going to assume that, not assume, but databases will always do this. They'll always build a primary key, an index on the primary key. And this lets us do things like, for a primary key, for a given ID, that's always a very easy operation to extract that one from the table. And similarly, if you want to add a new ID here, it's usually quite easy to add a new ID because you can quickly check to make sure that, yes, there's no other ID of this type in the data. Okay. Any questions there? Okay. And then finally, indexes do not have to be on a single column. So you actually could have an index on multiple columns that would, sort on one and then on the other, and that's fine. You can definitely have indexes, also primary keys, by the way, which we'll cover in a second, on more than one column at a time, or you can have them on one column at a time. So you can do them on both. If you have them on more than one column, though, you have to order those somehow. You can't have, a key on last name, first name would not be ordered the same way as a key on first name, last name. Right? Question there.
So the index table, is that abstract? Like, is that some sort of, like, is it stored in a B tree, or is it also available to you in another relational table?
Right. So the question was, is the index kind of abstract, or is it just stored somewhere that you use, or can you actually access it like another table? And it's more. I mean, it's not abstract. It's actually very much, instantiated on the actual disk. But no, you don't typically access them like other tables. They are hidden from view of the practitioner. Okay, so moving right along, let's talk about entity relationships now. And I'm going to be a little bit more vague here, because you can get very detailed here, and it can be an entire lecture on entity relationships, certainly. But I want to sort of discuss now how we use these primary keys and foreign keys to relate different entities. Or entities are, I'm using kind of, it's a formal term, but I'm going to use it kind of in the informal way. So before, a thing like a person is an entity, and a role would be an entity too. So those will both be entities. Okay, so let's just sort of jump right into what these relationships are. There are several types, sort of canonical ways that people talk about different entities, or different tables, really. Think of an entity as almost like a table, though it's not quite, so I want to be a little careful there. There are different types of ways that tables can relate to each other across tables. So you've already seen one, where we essentially had a role table, and we had a person table, and then we had a key in the person table that related to a row table, to role table. And these relationships take on many forms. There's the one-to-one relationship, which actually seems very simple, but almost never happens in databases, for a thing we'll talk about in a second. There's also a 1-to-0 one, which I don't usually see mentioned as a kind of a formal relationship type, but it's actually much more common than true one-to-one relationships across tables in a database. There are one-to-many, and then there's the converse and many-to-one. I'll give examples of all these, by the way. I'm just listing what they are. And there's a many-to-many relationship, which is probably the hardest to kind of instantiate and get your mind around, but it's not that hard either. So essentially, all these relationships relate one or more rows in a table with one or more rows in another table. That's what they're doing in the actual table sense. And as I said, it's important to know these are sort of actually relationships between entities, kind of in some abstract sense, where a person is an entity. You just happen to have a table that instantiates what attributes these people have. But think of them as actual relationships on the entities themselves, and it's just a little bit more intuitive that way sometimes. So I'm going to actually start off with not one-to-one, but one-to-many, because it's the one we've already seen. So we know that there's the role table here and the person table. And importantly, what's relevant for this circumstance is that a single role, one role, has multiple people that have that role, right? So the role-person relationship is one-to-many. And the way this is usually drawn is by these entity relationship diagrams here, where I'm not going to get too formal there, because there's all sorts of other things. You can have little markers that make them optional or mandatory and these kind of things. But if you see lines like this in a big, huge, enormous sheet of different tables, which is often how they're written when someone gives you a schema for a database, what this means is that the role there's an ID for the role, and then there's going to be a linking ID in the person table, but there can be multiple entries here that all share the same role. So the converse, of course, would be that the person-role relationship would be many to one. So that's just sort of depending on which one you say first. It's either one to many or many to one, but they're the same thing. And the way you actually encode that, of course, is just with exactly this foreign key in one table that links to the primary key in another table. So it's already very intuitive before you even mention this one-to-many business, but it'll be useful now, hopefully, as you sort of think about other types of relationships you can also have. Any questions? All right, I actually might make it through today. We're going at a good clip. All right, so let's talk about one-to-one relationships. And these, despite seeming very simple, are actually not used across tables hardly ever in a database for reasons I'll talk about in a second. So one-to-one is kind of the obvious thing. It means that every identity A has exactly one identity B. So, for example, if every person has an Andrew ID, we could have two tables, one person table and one Andrew ID table, and the Andrew ID table would just link the person ID for every person with an Andrew ID. Okay? Now, for a relationship to be a true one-to-one relationship, every person has to have an Andrew ID, and likewise, every Andrew ID has to be associated with one person, right? So there's almost, maybe actually, no point in having these be separate tables, right? Because we could just add another column in the first table, and that seems like it's doing everything you want to do. And in fact, that's always what happens in practice. And the reason for that is that this relationship is actually very hard to enforce kind of purely logically in a database. Because if you ever delete one entry here, you actually can't delete it because you'd have to immediately at the same time delete the other one over there. And so people typically don't do it that way. They will typically just add another column to that same table. It's a much more natural way to actually do this. You can hack your way around this and actually get like triggers that will fire to always maintain this exact form, but there doesn't seem to be that much of a point for this. It seems just easier in every way to just make a bigger table. The kind you will actually see more often is actually a 1 to 0 or 1 relationship here. So I'll talk now about, and I'm going to, for just this one slide, add these little dashes and circles, which just, if you look at these things, and we're not going to cover this at all, so don't worry, but what these actually are, these are ways of indicating whether or not the thing is mandatory or optional. So every person, they can have a grades or doesn't have to, but they can. So let's talk about this sort of conceptually, though. Let's say we wanted to add a grades table to our database, right? And the grades would link to a person ID that had the grade, and then they had to say their homework 1 grade, their homework 2 grade, etc. Right? We would add more columns as we needed to cover all the grades for the different homeworks. Now, importantly, not every person has to have a grade, right? Because I and the TAs, we don't get grades. So we're not going to appear anywhere. Our IDs will not appear in this table. Okay? This is still a 1-to-1 relationship when it exists, right? Because just because I don't have an ID doesn't mean that, one person should not have multiple entries here. It should be at most 1, but it does not actually even have to be 1. Right, so this is called a 1 to 0 or 1, or sometimes a 1-to-1 with an optional little circle there to indicate that it doesn't actually have to be instantiated. And as I said, don't worry about this notation here. Just you'll see the same things for one-to-many relationships and many-to-many actually too. Sometimes they'll have the little dashes and circles, but that certainly is going to be beyond what we talk about too much here. Yeah. Yeah.
So like here you said that you could easily just add another, add a greater column to this table.
Yep.
But like what if, let's say the uninvited table, let's say it has 4 other columns as well, like date of birth and stuff.
Yep.
Like that.
Right.
Then like isn't it more efficient to have separate tables and have like one table with like 50 columns?
Okay, so the question was, is it more efficient to have separate tables or one table, 50 columns? I wouldn't say it's more efficient, no, because you have to store the the data somewhere, right? And it's actually quite efficient to be accessing, if you're going to always access one and access the other, it's actually quite a bit more efficient to just have this all sorted in the same place locally so you get the whole record when you want it. So I think it's actually less efficient often. And you can certainly do it anyway if you want. Just be aware that it's not a true one-to-one relationship in the true kind of enforced sense, because you're going to have some probably small period where you add one table and add an entry to one table, haven't yet added it to the other one, and so in that time your database is actually in an inconsistent form. So you can, but it's just less common because you might just throw them all in one big database or one big table and then just filter the columns. Hide the columns you don't want to see it. You can always do that, right? Another question?
So in the grade section, so you could possibly enter a grade above 100 because that's not enforced, right?
Correct.
So the only way you'd avoid that is by again adding 1 to 100 in other tables.
Oh, I see. Yeah. So the question was, in this table, you are technically allowed to have grades be whatever they want, right? They don't have to be between 0 and 1. And I kind of before said, well, we don't want these roles to be arbitrary text. We want them to be some category. So so I'm going to make a separate table. And so do we have to do that again here? And the short answer is no. You can also add conditions on numerical quantities to say that these things cannot be outside a certain range. They have to be within a certain range. There's actually a lot of different data types you can have that are bounded data types that are not just arbitrary numbers. But the reality is oftentimes these things are only enforced by convention. So the database itself will actually not enforce, even with foreign keys sometimes, will actually not enforce that it has to be a primary key from their table. Just you better not insert one that isn't. And your application development on top of it doesn't ever do that, hopefully. Or if it does, there's a bug in it. And so hopefully things work out OK. And so oftentimes you can enforce bounds on them, but oftentimes it's more common for people just to kind of ignore that and do what they will do anyway. Yeah?
So the 1 to 0 relationship, this is implemented as a different table, right?
This one here, yes. So this grades table here is a different table than the other one. Now you could use the same table and add like null values for the ones that don't exist, right? Which is actually exactly what happens when you try to merge the things together, which we'll talk about at the end of this class or next time. But yes, I'm talking about a separate table now where there is at most one entry in the grades table for each person, but maybe not even one.
No, if that, the reason we had all the attributes in a single table for the 1-to-1 relationship was because we didn't want to have entries for values which don't exist. So that will even happen here. Let's say someone drops the course, and then the person ID is actually invalid. And then you will have grades for the person ID, which you do not have.
Right. So so the question was, I think I'm getting your question correct. Let me know if I'm paraphrasing it wrongly. The question or the issue here is that if people, for example, drop the course, you may still have an entry here that does not relate to any other entry in the persons table. So that's actually possible. Yes, you can have that. We'll talk about that actually later when we do joins. We'll talk more about that case. So this is not typically a foreign key. This is actually a primary key for this table separately. But it is still nice in some sense to have this ability to actually take back what I said before. Technically, it doesn't have to be, but I think to enforce this relationship, you still want it to be that way. Otherwise, it actually should be a circle on both places if they're both optional. The difference here is that if there's a lot of people that don't have any grades in your persons database, the only way to encode those in a single table will be to have null values for all their homework grades. For my homework grade or the TA's homework grades. And that's kind of a waste of space, right? Or again, and wasting space isn't really the bigger issue here. It's sort of conceptually, you don't want to have a null grade for all these people. You want to have just one big file with nothing else, right? So I think it's actually, personally, and this is, I think, to a certain extent, kind of based upon, your own personal feeling of what makes sense as a data model here. But personally, I think it's actually OK to have people that have dropped the course no longer be in the persons table, but still have a grades entry. Or maybe you leave them in the grades entry in the person table, and you just have a flag where they've dropped the course or not, right? So yes, they submitted some assignments, they got a grade. We shouldn't discount that entirely, but we want to somehow flag the fact that they're no longer in the course. So it can preserve things that are kind of nice like that, which actually would be hard to preserve otherwise, that I think can actually be a positive thing a lot of times. Yeah.
Yeah, it's some kind of question. So in all previous tables, we had that ID column.
Yeah.
So
Okay. Yeah. So the question was, what happened to our ID column here? We're missing that, right? So you could actually have a separate ID column that sort of says, this is just my ID of the grade entry, right? I'm going to have a separate ID column here, separate from my person ID. That person ID is going to be a foreign key linking to something else, right? So yes, you can do that. I don't here because it's a little simpler. Because it's a one-to-one relationship, you can actually use the same ID as the primary key here as you were doing from the other one, but I wanted to call it a person ID to emphasize the fact that it is, in fact, kind of linking to that other table here, other table there, even though, depending on how you set it up, it may or may not be a true foreign key or not. You can certainly have keys, though, that are the same primary key across multiple tables. There's one more question. Yeah.
It's actually kind of similar to his question, but so how do you refer, or what's like the pointer into the grades table from your person table?
Right. Okay. So the question is, what's the pointer into the grades table from the person table? And that,
You might not have foreign.
yeah. And well, again, that is actually the person ID. The ID in this table is the same as the ID in the other table. So we're using the same IDs. So we are using them as the foreign key. Maybe I should just say they are going to be foreign keys. The only qualification there is later on I'm actually going to violate that a little bit so that they're not technically enforced foreign keys, but you can think of them as foreign keys, and that this ID here is the same as the IDs in the person table. And that lets us link them kind of easily without having to having to have a separate ID for this one and then a separate person ID. For one-to-one, it's kind of handy. Obviously, for many-to-one, you couldn't do that, right? Because you couldn't have the roles table have a one-to-one correspondence, or even a 1-to-0 or 1 correspondence with the person table. All right, so the last one, which is kind of the most fun in some sense, is the many-to-many relationship. And this is a case where one row can have many items in another table, and one item in the other table can have many items in the original table. So that's kind of confusing, so let me just illustrate it with an example. So consider instead of having a single table like this that listed all their grades and had grades separated out column at a time, that's kind of a pain because if I add a new assignment, again, a pain is all relative here because it's really easy to do actually, but suppose I don't want to have to add a new column to my table every time I add a new assignment, right? For whatever reason, I just don't want to do that. What I can do instead is build a separate homework table that has its own ID and one entry for each of the homeworks that I actually release, right? So homework 1, homework 2, and now if I want to add another homework, I just add another row to this column, to this table here. Okay? So this is my homework table, and I have a person table, and each person will do many homeworks, and each homework will be done by many people. Okay? So the way you actually represent that relationship is you build an additional table that's called an associative table, sometimes a cross-reference table too. And with this table, this is what I'm calling the person homework table here. And it's going to have two IDs. It's going to have a person ID and a homework ID. These are going to be foreign keys that point to an entry in the person table or an entry in the homework table. And then they're going to have a score associated with that. All right? So this actually encodes the exact same information before. So student 5, their homework 1 score is 100. Their homework 2 score is 80. Student 6, their homework 1 score is 60. Their homework 2 score is 80. But I'm doing it in a way where each row only encodes one of the scores, not all the scores for that person. Okay. So now the question is, and I will just ask this of people, what's the primary key of that table? Yes. Yeah, so the answer was, it's called a compound key. Shouldn't it actually, it doesn't matter if you know that name or not, actually. The key is both those two columns there, right? Because the thing a primary key does is it identifies unique rows in the table, right? That's what it does fundamentally. And we cannot have, well, we can have, more than one entry of this, of more than one homework score for person 1, because they can have a score for homework 1 and homework 2. They cannot have 2 scores for homework 1, right? No person can have 2 scores for homework 1. So the elements that have to be unique in this table are both this column and this column. And that makes up the foreign key. Sorry, the primary key. The concatenation of both those two things makes up the primary key. Now, what are the foreign keys in this table? What was that? Yeah, so both of those separately, though, are foreign keys, right? Because they both point to the primary key in some other table. Okay, now sort of the real question here. What indexes do you think you'd want to create on this table? So first of all, what will be created automatically? What index exists immediately? Who said that? The primary key, right? So there was already an index over both these two things jointly. And a joint index works something like, you can think of it as sorting one, then sorting the other based upon that, and it just does both of those two things. Do you want anything else on the index? Do you want to create any other indexes? It's always hard for me to say. Do you want to create any other ones? Sorry, I'm not, people answering? What was that? On a score, I guess you could, yeah. If you want to sort of always know like what the top scores are, you could do that. It wouldn't hurt. But yeah, so certainly you could create it on the scores, yeah, because that way you could sort of easily say who has a score of 100, or what's all the assignments that got a score over 100. Were there any others you want to create?
I mean, if I want to scores for all homeworks for one person, then like if I can extract that information from that sorted tree of the pairs, that's fine. If not, then I want a separate one.
Yeah. So conceptually, and oftentimes you can kind of combine these two things in the actual database combines them, but conceptually you actually do want a separate index on each of those two columns. I mean, presumably, or at least it would be useful to have that, I'll say, right? Because that would let you quickly say, okay, what are all the scores for this person? What are all their homeworks, right? If you don't have that, I mean, again, ignoring kind of how the joint index is stored, just think if you don't have an index over a certain column, you can't search on that column other than scanning through the whole table. So if I want to know what are all the scores for person 5, the way to do that is to create an index on that person, right? And similarly, if I want to know all my scores for all people for homework 1, the way to do that most efficiently is to have an index on that one. And in fact, that one you have to create one or the other to do it efficiently, right? Because your joint index would only cover one of those two cases. It wouldn't cover them both. So typically, it's more common actually just to go ahead and create an index on both those two items. So you can quickly search through all of these things. And the score, too, might as well do it on all of them while we're at it. So have indexes everywhere. Yeah? Yeah, so the question was, can you combine, can databases combine the joint index to get one index? And yes, you can do it one way, but you can only do it one way, right? A typical index, again, it depends on your data structure here, but typical index will sort by one thing, and then after that sort of thing, they'll sort by the next one. So you can't, so if I sort by person here, and sort of have it like this ordered, right? That's my sorted list. It would not be that easy to find, say, all homework 1s, right? So I want a separate index on homework 1 in order to do that. So oftentimes the way they're doing it internally is actually by having separate indices. I mean, again, you don't have to, but I actually would recommend you just do it, because it should not actually cost you extra space if you do it, but it is a better idea conceptually to actually have separate indexes, even if they're doing it internally already. That's sort of an implementation detail, whether or not they do that by default already. Conceptually, you still want them. Okay, so the way you draw a many-to-many relationship is with this the many relationship side on both entities. So here, a person can have many homeworks, and a homework can be done by many people. And just to sort of clarify, we could also relate this in terms of an associative table. So we could also actually make explicit our table here and say that one person has many entries in this table, and one homework has many entries in this table. And that's actually equivalent to this relationship up top. But the only difference there is, wait, no, did I write this backwards? No, this is right. OK. But this is kind of, I actually don't like doing this because this is a little bit getting into kind of the details of how it's implemented. Conceptually, what's really happening is that you do just have this many-to-many relationship that happens to be encoded with an associative table, not that this is somehow some part of your data model itself. You actually, typically, when you write these entity relationship diagrams out, it's a little cleaner to write them in terms of the actual entities themselves, not some associative table in addition. OK, any questions before we go before we move on? OK, so next I'm going to talk about two libraries for dealing with relational data. And actually, this is what you'll mainly be working with on your homework, at least the one question on your homework, is working with these two libraries. So we're going to work with libraries called Pandas and SQLite. And it's pronounced SQL, by the way. Some people say SQL, but I think you can say both. But typically it's pronounced SQL. So whenever you hear whenever you see SQL, it's typically pronounced SQL. I'll talk about what that actually is in a second. OK, so these two libraries. Actually, who here has used Pandas before? What about SQLite? OK, it's actually a good mix. So some people use one and not the other. So that's excellent. Pandas is actually probably it's somewhat it's a horrible error to introduce it in a lecture like this because it's not actually a relational database, or it does not actually store relational data. Pandas it does or does not. That rather. Pandas is actually it's a wonderful tool, but what it actually is in some sense, you can think about it as kind of like a wrapper for matrices that let matrices have names for their rows and their columns. Or kind of like indices for their rows and their columns. So it's not actually a relational database or even database system. For example, it doesn't really have primary keys. Is one major thing, right? Sort of a big clue that it's not actually a relational data system. But it does actually have a lot of functionality that's essentially mirrors or mimics what's in a relational database system. And it's a tool that's very useful in practice. And so we're going to actually cover it here in terms of how you use it to kind of mimic some of the functionality of a relational database. Right? And we're also going to cover it in more detail in other portions of the course. And it's a very handy tool to use a lot in a lot of data exploration. So that's why we're covering it now. But I do want to emphasize that it is not actually encoding relational data. This is different from SQLite, which actually is encoding relational data. So that one is OK to call a relational database. All right, so let's talk about Pandas. So the main object in Pandas that you'll deal with is called a data frame. As I mentioned, a data frame is essentially like a table, right? It has rows and it has columns. And the rows have names to them. The rows have indexes or numbers. And the columns also have names to them. So what I'm doing here is I am creating a data frame with these entries. So this is going to be my ID entry. This is going to be the last name, first name. I'm leaving out the rules for now. We can load those later, but it gets boring typing these things up too much. Besides, you'll never have to type them in like this. You'll always just read them from a CSV file or from a database. And I'm also adding column IDs. And I guess I actually made a mistake here. I should probably just put ID there instead of person ID, but oh well. So I create the data frame. So this creates a data frame that has 6 rows and 3 columns. And the next thing I do is I set the index of this thing to be a person ID. Now, Pandas, intentionally, I don't mean it's not a mistake, but what it does is it kind of confuses indexes and primary keys. So in Pandas, you typically refer to rows by their index, not their primary key. And you have to treat indexes and other columns differently. Right? So we'll see a lot more of this later, but just know that it's doing kind of a weird thing here. This is kind of like relationally setting a primary key on that, but in pandas is actually an index. And that also, by the way, encapsulates the index part, where you do, in fact, have a fast way of accessing it when you set an index. But it's much more like an index and primary key combination than just an index alone. And the best way, by the way, to get familiar with all this is just experimenting. So just fire up your Jupyter Notebook, run pandas. You'll have to do it for the homework anyway, so do it before then, maybe, if you want to get a little bit of practice with it. But basically how it works. And then if you type if you're in Jupyter Notebook and you just type the data frame name itself, I call this DF with my data frame for data frame. If I just type this, it'll actually print a nice little, nicely HTML stylized representation of your table. Okay. So here, this says the person ID is the index, and it has two columns called last name and first name. So the big difference also here is that once you set something as an index, it's no longer a column as far as pandas is concerned. It's something different, which is very odd, kind of, and very different from databases. But it works in a different way. It's kind of encapsulating a different sort of paradigm. So it works there. Yes, a question.
If it's so different from databases, you said it's kind of like flake key in terms of how you refer to indices, primary keys. Why is it used?
Why is it used? The question is, if it's so flaky like this, why is it actually used? So pandas is very nice for doing quick in-memory data analysis where you want essentially a matrix structure, but you want it to be indexed by rows by some index, and you want also to have names for your columns. So most, say, machine learning, right, algorithms operate on a matrix formulation, but it's very unintuitive to say, oh, that's feature 1, that's feature 2, right? You want to say that's last name and that's first name. What data frames give you is a nice way of thinking about a matrix while being able to indicate what the different entries actually mean. And that's not all that it is. It does more than that too, and it does do actually a lot of functionality that works just like a database. So you can do things, you can take like these matrices and do things like merges and joins, and which we're going to talk about in a second, that are sort of database operations. So what it does is it kind of spans the gap between databases and matrices in a sort of relatively lightweight in-memory format. So it's very nice for that. And because of that, that kind of is a lot of what you want to actually do quick data analysis, and that's why it's become so popular. So the implementation of pandas under the hood represents these things as matrices, yeah. You actually can access the matrix representation of your data at any point.
So yeah, if I want to get the information from some entry, I can use like personal ID and last name as a string to access.
Yeah, let me talk about how you access it in a second, because there's if I can convince everyone to use a certain way of using pandas, it'll be a huge success here. So we'll talk about it in a second. Some important notes. As I mentioned, I'm going to stress this again and again because it's very important. But pandas is not a database system. Don't think it's a database system. It just happens to mimic a lot of the functionality of database systems. The second big thing, probably most errors you will see are from these two items here. The most errors you will do on your homework, for example, are from one of these two items, if you don't listen to them at least. Hopefully everyone will listen, we'll have a different class of errors, but if you don't, this will be what's causing all your errors. So the first thing is that most operations in pandas are not in-place operations. They take a data frame, do something like set an index of it, right? But if I don't have this in-place equals true, what it will do is it will return a new data frame that has that index set, but not touch data frame itself. So data frame.setIndex will return a new data frame that is like this original one, but with person ID set to be the index. So if I don't set in place equals true there, that's what I get. if you actually want to modify your data frame in place, you have to call these in-place routines, or call things like df equals df.setIndex person ID. And sometimes you actually have to do that. There's some operations that don't have the in-place modifier, so you have to do it anyway. And the reason for that is kind of actually because of this underlying matrix structure. Matrices are not easily modified, and so this is why everything is actually done this way. Question over there.
Is the primary difference, well, the main difference between primary key and index, that a primary key uses a foreign key?
So the question was, is the primary difference between an index and a primary key the fact that a primary key can be used as within a foreign key? Not really. So they're really kind of two different things in some sense. So an index is about fast access. So you can have indexes on every single column in your data if you want, in a database, right? They're really about fast access. And they're not necessarily unique. So there can be an index over a column that has repeated values. Pandas will be fine in some cases. Sometimes it forbids it, but for the most part, actually, you can have multiple. You can have an index with multiple with repeated entries in it. That is actually allowed in some cases. Sometimes you try to insert things there; it'll do weird things, but it can actually support indexes with multiple repeated entries. So they're actually somewhat different conceptually, and I think it's important to know that the Pandas is kind of treating them in similar ways, but more like an index. Honestly, it still is more like an index. So number one, in place. For the most part, everything is not in place. And those in place things usually just do exactly what I said. They just set data frame to equal to data frame plus this thing. Yeah.
Can you repeat once again what is the motivation for using for implementing all of the operations in Pandas not to be in place?
So the motivation for that is that the underlying data store behind Pandas are matrices, not trees, or not trees that where you can easily insert or remove items. They're sequentially stored memory sort of blocks in memory, and so these are actually not that easy to add new elements to. I mean, they can be depending on how you organize it, but they're theoretically, at least, matrices are not meant for easy concatenation or easy modification of the data. So if I remove a column, it's actually set it as an index. It's actually a very expensive operation because I have to remove it from every single row. It's an order n operation here. So because these things are actually kind of destructive in nature, they change the underlying data, the way it's stored. They are kind of to enforce that or to remind you of that. They don't have in-place operations be the default. There was one more over there.
One more efficient over the other. You could just reassign it to the same variable and have the same. You don't need to in-place flag. You could just reassign it to the same variable, right?
I see. So the question is it more efficient to use the in-place or not? They're exactly the same. Yeah. If you say df equals df.setIndex, the thing, it's the same. Maybe there's been some optimization that I don't know about, but I think actually that's what it does under the hood. It just sets it equal to the new thing. Okay, so the second thing is when you select a single row or a single column from a Pandas data frame, you will get a different type of object back. This object is called a series. So Pandas represents differently two-dimensional data and one-dimensional data. A series is a one-dimensional data frame, kind of, but it's actually a different object that has different calls and different behavior. For now, I'm going to just put it at that, and you will and in the homework, when you get one of those things, we will talk about what you do with it and how you treat it differently. But just be aware that if you ever take a slice of a data frame that only spans a single row or a single column, you will get back a different type of object called a time series, or sorry, that's a series. Time series are often represented like that. But that's a separate topic. Called a series that has different sort of usage than a data frame. So just be aware of that. And if your code's throwing some error because you can't call some function on this thing you returned, it's very likely because you're trying to apply an operation to a series that actually is meant for a data frame or vice versa. All right, so let's talk about some common commands now you can do in Pandas. And by far the most common command, I think, is read CSV. So you load a CSV file into your data frame. We'll show you in a second. There's also a very similar one you can do to load a database table into your data frame. So the reality is databases are great, but even SQLite, which is very nice, is a total pain to actually operate on, right? Like when you want to get some quick operation on like a whole entry of a table, it's kind of a pain. So what I often do, actually, talking about why would you ever use Pandas, is I will actually just load that query into a Pandas data frame, operate on it there, and do my analysis there. It just tends to be easier. Keep all my data backed in a nice actual database, but query it when I need it. And this is actually, I should say, these are a couple functions. We're going to talk about a few more, I think, on Wednesday in visualization. And we will also detail a few more in the homework. But this is not meant to be exhaustive at all. It's giving you the list of things that you might want to do. .head is a very good call, too. That returns the first 5 rows of that table. So if you do want to commonly print your tables there, your data frames, typically you don't print the whole thing, because that could print a very long thing. They will truncate eventually in HTML, but it'll go like 100 rows or so. Just type df.head instead, and then that will only print the first 5 rows. OK, now the actual important things here. This is how you access elements of a data frame. So the key rule here is always use the .loc command, .loc for location. Do not access a data frame by df and then open brackets by itself, except in a few cases, which I'll denote next week or next lecture. Do not do that. Always use the .loc file or the .loc call. And the reason for that is there's a lot of things that are much nicer, that happen much more, sort of much cleaner when you do it this way. The first thing, and the other thing, is always specify both a set of rows and a set of columns. So the .loc function works the same way. It takes as its 2 arguments, and it's actually brackets here, not parentheses, it's brackets. But it takes a list or a single element or a colon for both the first element and second element. Okay? So if you specify a colon, that means just everything. Right? That means all the entries of that row or of that column. You specify a single element here. So last name, or for the first one, you specify like a 1, right? Because that's the index of the rows. In our case, that would be referring to the first row here. How much time do I have? I'm running out of time quickly here, aren't I? Okay. If you specify a single index there, it will return a series with that 1 column or 1 row. Or if you have 2 things, it will actually return just the element of that, just the 1 element in that row and that column. If I specify a list of things, it will actually return a data frame that contains those elements. So you can do things like these 2 are actually, the first 2 are actually different there. The first one returns a series of all the elements of last names. And the second one returns a data frame with 1 column, and it only includes last name. So honestly, the only way to get familiar with this is just to experiment on your own. So fire up your Jupyter Notebook, type all these things in, and see what they actually all correspond to. That'll be the best way to learn this. But always, I mean, the high level thing here is always use the .loc, both for getting attributes and for setting rows and columns, both for getting rows and columns, indexing into them, and for setting them. Yeah.
I've used something called .ix, which kind of allows a combination of .ilog and log.
Yeah, so I don't like I think .ix has some ambiguities there, so I don't like it as much. I prefer everyone use .loc. Because it's ambiguous sometimes what you mean by .ix. And I think it's actually, isn't it deprecated also? I thought they were actually getting rid of it. I think so. I could be wrong. It could be the other way around. But I think it's being, because it's sort of unclear sometimes what it means. Like if you have an integer index, do you mean the iloc or do you mean loc? I think people are sort of getting rid of that. So I would say use loc and iloc. Is it? Oh, good point. It's rows, comma, columns there. Thank you. Yes.
So, so the columns, is it by number of columns or is it by ID?
Yes. So it's always by index, which is kind of like by ID, right? The dot lock is always by index. If you want to access them instead by their number, that function is called ilock. So you can access them also by their number, by their, I want to use the word index here, but by their integer index, right? So 0 always starts at 0 and then goes up to the number. You can access that with ilock. And you can pass the same thing. So you can also, in ilock, you can also have a colon. You can have a list of integers that also all works. But it makes it much easier. As was mentioned, you actually can mix them with other calls. So you can have some be integers and some be like numbers and some be integers. I would recommend no one do that. Not in the homework, at least. If you want to go off and do your own stuff in Pandas, you're welcome to, but don't do it in the homework. And finally, you can also do things like add new rows. So I actually add addition. So there's no index 7 so far, but I can actually add a new entry using .lock. And you can change the text in one, so I can change my last name to Kilter instead of Coulter, and it all kind of works nicely as you would expect. If you don't do that, if you try to index without the lock command, you will find odd things happening. You will create like a series that you can then change, but then don't change the underlying data, and all sorts of things happen that are nasty. Yeah. It takes the rows first. Sorry, the question was, does df take the rows or columns first? This is a typo. It's rows and then columns. Remind me to change that, because that's actually that's a big deal. Definitely rows first and then columns. Okay, so I'm almost out of time. I'm not going to try to go through this all. I will cover it next time as well. I will get a high level here to start with, and then we'll talk about finishing. We'll finish this up next time. But the other system we're going to use is called SQLite. And SQLite is an actual relational database. It really actually is a full relational database. It's very, very nice. And part of the reason why it's so nice is that unlike most databases, it is completely serverless. Meaning that if you set up, if you ever use something like MySQL or PostgreSQL, you'll know that it's a total pain because you have to sort of run a server process that has its own authentication and access rights, and then you have a client that connects to that and then issues commands, and you have the wrong access rights, etc. And so SQLite is nice, and it kind of glosses over all of that and uses essentially just the file system of the actual OS to control all access, to control all actual reading and writing to this. So what you do is you actually create databases that just belong in single files on your system, which is not how PostgreSQL or MySQL work, but it's very nice when you have relatively small databases. Will not scale. You're not talking about storing multiple things across multiple machines here on a big cluster. We're talking about things that can fit into a relatively small single machine, which is actually, disk on a single machine is pretty big these days. It also does, but it does, however, allow for things like simultaneous communications or simultaneous connections to this. So multiple different applications can open up the same database file on your disk and read and write from it at the same time. Of course, writing you have to block while you're doing the actual write itself, but between these things, they can all, for example, read at the same time, be issuing queries at the same time. So it does handle some degree of concurrency. Now, it's not quite as sophisticated in terms of concurrency as real client-server models, of course, right? Those spend a whole lot of time trying to guarantee certain conditions, and oftentimes failing in the distributed architectures, trying to guarantee certain conditions, like if I issue two writes that kind of look like they're coming at the same time, what do you do then? How do I know who has priority, etc. So concurrency in general in databases is extremely hard and extremely difficult to get right, but SQLite does handle some subset of that. All operations in SQLite, as the name would suggest, use SQL, the language, which stands for Structured Query Language, which essentially is a little language for writing and reading from databases and issuing queries to databases. We'll talk about this a lot more, a little bit more next lecture, at least when we finish up this unit here. But essentially a nice scripting language for issuing commands to a database. And finally, you actually can enforce foreign keys in SQLite, but we won't bother. So after going through all this about how great foreign keys are, because they enforce these things, you actually we're going to set up things that are foreign keys technically, but we're not going to worry about that fact when we actually build a database. We're just going to ignore it and assume that if we don't do that, then something maybe goes wrong. But we, let our app figure that out. I think I will end there. It is, well, actually, first, any questions? I have like 1 minute left. Any questions? Yeah, over there. What was that? Yes, so the question was, can you do multiple index? Can you index on multiple columns in Pandas? Yes, you can. And it gets really nasty. How you access those things, and they change the notation for how you access them too sometimes. There's one more question, but I think I'll pause for now. For the people that are having lunch afterwards, just come hang out around here while we before we head off, and we'll head off to the IC or the UC in a second. Well, there are 2 signed up right now. We'll see how many there are right now during the lecture.